When a massive volume of data hits a single network uplink, you get a severe, crippling bandwidth bottleneck. The obvious solution is to plug in more cables, but in a Layer 2 network, adding redundant physical links creates a disastrous bridging loop. To prevent those loops from crashing the network, the spanning tree protocol steps in. STP systematically identifies parallel connections and mathematically blocks them to ensure there is only one active path. In this diagram, two switches are connected by four distinct parallel cables. Because of spanning tree, three of these cables are forced into a blocking state, dropping all traffic. You are left with a single active path, wasting 75% of your potential bandwidth. EtherChannel bypasses this physical constraint. It groups those four separate cables and envelops them into a single logical pipe called a port channel. By tricking the switches into seeing these multiple physical connections as one single interface, spanning tree sees no loop to block. All four cables are allowed to forward traffic simultaneously. While this solves the physical bandwidth problem, it creates a new architectural challenge on the control plane. Both switches now have to perfectly agree on exactly which cables belong in this unified bundle. If two independent devices are treating four separate physical links as one entity, how do we verify they are bundling the right ports together? Historically, administrators used static EtherChannel. This method manually forces ports into a bundled state without asking the switch on the other end any questions. If a technician accidentally plugs one of those forced cables into the wrong device, or if the configuration on the remote end doesn't match, the local switch won't know. It will blindly forward production traffic down that misconnected link straight into a black hole. To eliminate that risk, modern networks rely on the Link Aggregation Control Protocol, or LACP. LACP is a control plane protocol that actively negotiates and verifies the connection. It ensures both switches agree on the parameters before a single byte of user data is allowed to cross. To keep the terminology precise, EtherChannel is the broad link aggregation technology. The port channel is the resulting logical interface, and LACP is the specific protocol that safely builds and maintains it. Before the bundle forms, LACP initiates a conversation. The switches exchange control messages called LACPDUs. These exchange strict identity markers, confirming they are connected to the correct partner and that these links belong in the exact same bundle. This negotiation verifies configuration parity, demanding identical speed, duplex, and trunking behaviors. If a mismatch occurs, like differing VLANs, the interface cannot route predictably. LACPDU detects this and immediately halts negotiation on that specific wire. The protocol will not automatically fix bad network administration. It protects the network by refusing to bundle misconfigured links. The LACPDU conversation acts as a strict architectural bouncer. It demands perfect alignment before it opens the logical data plane. To control how this negotiation happens, LACP uses two behavioral modes, active and passive. In active mode, the port operates as an initiator. It actively broadcasts LACPDUs to ask the other side to form a bundle. If both sides are active, they initiate the conversation, agree on the terms, and successfully form the EtherChannel. Passive mode is a listener.
It never speaks first, but responds to LACPDUs. Therefore, an active-passive relationship works perfectly, completing the negotiation. However, the fatal error is passive-passive. Both devices stand dormant, 0 LACPDUs are sent, and the bundle completely fails to form. Dynamic negotiation relies on a simple rule. To build the connection, at least one side must initiate the conversation. Once formed, a common misconception arises. Combining four 1 gigabit cables does not create a unified 4 gigabit pipe for a single file transfer. If you took a single file and sprayed its packets randomly across cables, they would arrive out of sequence, destroying performance. Instead, once LACP establishes the logical link, the switch hands traffic distribution over to a hardware load balancing algorithm. The switch evaluates incoming traffic, running a mathematical hash on parameters like IP or MAC addresses to sort it into discrete flows. To guarantee strict frame order, the algorithm pins each entire flow to exactly one physical member link. This design means a single user's file transfer cannot exceed the maximum speed of the one physical cable it is assigned to. However, 4 different users can operate simultaneously at full gigabit speeds without congesting each other's traffic. LACP and EtherChannel are designed to provide greater aggregate capacity across the entire network, not increased maximum speed for a single session. The job of LACP isn't finished once the bundle is online. It continuously sends LACPDUs across the active links to monitor the health of the connection. Consider a bundle operating under heavy enterprise load. Suddenly, a transceiver dies or a physical cable is severed. In a static, non-negotiated bundle, the switch might not realize the path is completely dead. It would continue blindly dropping active traffic down that broken link. LACP instantly detects the missing LACPDU heartbeat, suspending the failed link while keeping the broader port channel online. The switch's load balancing algorithm immediately recalculates, taking the traffic flow from the dead link and seamlessly redistributing it onto the remaining healthy cables. By constantly monitoring the physical layer, LACP decouples logical connectivity from physical hardware vulnerability, giving the network invisible redundancy. Network architects can leverage this self-healing behavior with an advanced control called minimum links. Imagine a critical 40 gigabit trunk that loses 3 of its 4 cables. Limping along at 10 gigabits might cause severe application timeouts, which is often worse than allowing the network to completely fail over to a dedicated backup routing path. The minimum link setting allows an administrator to define a critical bandwidth threshold. If the number of active links drops below that limit, LACP intentionally tears down the entire logical port channel to force a clean failover. Understanding this architecture requires separating 3 terms that engineers frequently mix up. EtherChannel is the underlying aggregation technology, LACP is the active control protocol, and the port channel is the final logical interface. LACP has become the universal standard because it is vendor neutral. It verifies configuration parity before forwarding data, and it ensures dynamic self-healing when hardware fails. LACP provides the architectural intelligence that forces the physical layer to serve the logical design safely